interferon gamma, you really want to have that present, but it's a double-edged sword because it will upregulate PD-L1 on the tumor cells. And now you activate or you bring into place an inhibitory axis that the tumor is using to really cause a suppression of those functions in the TCR-Ts that you're bringing in. How can you combat that? And we decided we would work with the concept to turn that deficit that happens in a TCR-T when it interacts with the PD-L1-positive cell into an asset. And that asset is our switch receptor. So it goes back to nature's selection for a natural PD1 extracellular domain that interacts in the same off and on selection with PD-L1 as nature has designed the system. You know, those affinity of those interactions is not modified. But what is modified is the signaling apparatus through the PD-1 molecule in the T cell has been exchanged for the positive co-stimulatory pathway 41BB. Now, 41BB is a really good co-stimulatory pathway in CD8 T cells. It runs independent of the T cell receptor. So when you have a recombinant T cell receptor, which is driving your peptide MHC interaction and giving you your first signal, and then you bring in such a switch receptor, we want tumor cells or other cells in the tumor microenvironment now to express PD-L1 because then they amplify the activity of our TCR-Ts. And it's the combination of these two pathways, the starting signal through the T cell receptor with the switch receptor, brings some really remarkable properties to the T cells. It's not necessarily so dramatic in terms of the cytokine secretion or the killing, because we've already controlled that by choosing a really excellent T cell receptor, but it's other properties. So for example, we try to model a little bit what happens to a T cell receptor in a solid tumor microenvironment by using three-dimensional spheroid cultures. And if you just have the standard TCR-Ts, we call them naked TCR-Ts, so they've got the receptor for the specific targeting, and you give a population of those cells a tumor spheroid and make them kill it, and then as soon as they've finished, you throw another one at them and make them kill that, and then you throw another one, they will become exhausted. You can see it appear just before your eyes. But if you have the switch receptor brought in on the same vector, so every T cell that gets a TCR gets the switch receptor because they're co-expressed, then that sequential exposure to tumor cells goes on and on and on and on and on. So that shows you that you can overcome, as closely as we can test it in vitro, you can overcome the exhaustion that occurs from just constantly signaling a T cell. And then there's a dramatic impact on the metabolic fitness of the T cells. The mitochondria stay intact, their mitochondrial signaling is retained, they can survive in low oxygen, they can survive in low glucose, they become resistant to TGF-beta, all of these properties, just with putting these two simple tools together, really gives you a TCR-T product that has a much better chance to function well in the tumor microenvironment. And that's how we use, if we're going to mobilize high interferon gamma in the tumor microenvironment to have all of these marvelous impacts, how we dampen that negative impact of putting PD-L1. And now, of course, we would like that to happen. Even if the tumor cells themselves don't naturally express PD-L1, if the TCR-T upregulates it, then it upregulates its chance to get co-stimulation. And it's that combination of both, which we think is really cutting edge for solid tumor indications. And once we had this system put together, then we decided we would really pivot our programs to bringing this forward into the clinic as fast as we can.